So in this video, I'll be explaining the concept of conditional probability, and I'll be also discussing a famous probability puzzle called as Monty Hall Problem and how we can approach that problem using conditional probability. So what is conditional probability? It is the probability of occurrence of an event when another event has already occurred. Let's say there are two events A and B. So what is the probability of A when B has already occurred? So that the formula is given by probability of A when B has occurred is probability of A and intersection of A and B upon probability of B. So here is the famous diagram known as Euler's diagram. So this represents the universal set with a probability of 1. These are different events A, B1, B2 and B3 with respective probabilities. So the B1 here has the probability 0.1, B2 has the probability 0.12 plus 0.04. Uh, this is the event A, which has the probability of 0.3 plus 0.1 plus 0.12. Similarly, B3 has a probability of 0.1, and this uh, the universal set minus all these sets has a probability of 0.34. So what's the probability of A? It's 0.3 plus 0.1 plus 0.12, as already told before, it's 0.52. The probability of A given B1, that is, what is the probability that A will happen given B1 has already happened. So since B1 is entirely inside A, the probability will be 1. Uh, Next, what is the probability of A given B3 has already happened? So in this diagram, we can see here that A and B3 are disjoint. That is, they have these two events have nothing in common. So the probability of happening of A when B3 has already happened will be 0. Next, what is the probability of the occurrence of A when B2 has already occurred? So this will be given by the probability formula here. Probability of A intersection B, which is 0.12. This intersection has a probability 0.12 divided by probability of B2 here. So the probability of B2 is 0.12 plus 0.04. So the probability will be 0.75. So let's discuss one more example to understand the concept of conditional probability better. So here we define two events. First is the event when sum of the faces on the die, two die is even, and the second event is when a second die shows a 2. So this diagram here shows the different possibilities, that is all our cases, sample space basically. And this diagram here shows the possible cases, that is it sums up the numbers on the two die. Like let's say these are the numbers on die 2, these are the numbers on die 1. So if the die shows 1 comma 1, so the sum is 2. 1 comma for 1 comma 2 it will be 3, and similarly let's say for 3 comma 3 it's 6, 4 comma 6 it's 10. Similarly, so it lists down all the possibilities. So let's say we are interested in calculating in finding out what's the probability of occurrence of S2 when E has already occurred. That is, what's the probability of let's say what's the probability of that the second die will show a 2 uh, when we know that the sum of the numbers on the two die displays is even. So our total sample space includes only those possibilities when the sum of the numbers is even. So these are all the possibilities. Half of these possibilities, the sum is even. So out of 36 cases, we have 18 favorable cases. Now, using the formula, what will be the intersection of S2 comma E? It will be all the cases from here when the second die shows a 2 and the sum of the two numbers is even. So this is 2 comma 2 when the sum is 4, 4 comma 2 when the sum is 6, and 6 comma 2 when the sum is 8. So these are favorable cases. Hence the probability is 3 upon 18, that is 1 upon 6. Next, we are interested in finding out what's the probability of the occurrence of E given S2 has happened. So our total favorable cases is 6. It has reduced to 6 from 36 when the second die shows a 2. So from these 6 cases, what are our favorable cases? When the sum is even. So as explained earlier, it is only there are only three favorable cases, that is 2 comma 2, 4 comma 2 and 6 comma 2. Hence 3 upon 6, which is 1 upon 2. So what important message that this examples gives us is that probability of occurrence of A given B has already happened is not equal to probability of occurrence of B when A has happened. So these two probabilities are not similar. As we can see here, one is 1 upon 6 and the other is 1 upon 2. So Monty Hall problem is a very popular probability puzzle, and it is based on one of very popular TV shows of the 70s, American TV show. So it's a game show wherein, let's say there's a contestant and there's a host. So a contestant is asked to pick a door. So behind one of the door is car, and behind the other two doors are goats. So as a host, I know that what is behind each door, and let's say you are the contestant. So I ask you to pick a door. Let's say you pick a door, you pick the first door. I know what is behind every door, so I open door 3, behind which is a goat. Now I ask you whether you want to switch to door 2 or you want to remain at door 1. So we need to find out what is advantageous. Like, let's say what is the probability of winning if we switch to door 2, and what's the probability of winning if we remain at door 2. So we'll explore this using the concept of conditional probability. So we will now solve Monty Hall problem using conditional probability. So in the previous slide, we saw that the contestant has chosen door 1. The probability that the car is behind door 1 is 1 by 3, and the probability that car is behind either door 2 or door 3, the combined probability is 2 by 3. Now the host has already showed that there is no car behind door 3. Hence the probability that the car is behind door 2 is 2 by 3, since the probability that car is behind door 3 is 0. We know that already. Hence, if we make a switch, the probability of winning is 2 by 3, and if we remain at door 1, the probability of winning is 1 by 3. So it's advantageous to switch rather than to stay at the same door. We'll see this from a decision tree and the conditional probability concept. So here the player has picked door 1. Now the car can be located at door 1, door 2 or door 3 with equal probabilities here, 1 by 3 each. Now, let's say the car is located behind door 1. The host will open either door 2 or door 3 with equal probabilities of 1 by 2 each. So the total probability becomes 1 upon 6 in each case. Uh, for this case, if we stay, then we'll win, and if we switch, we'll lose, because we are already at door 1 behind which there is car. All right. So now we know that we have picked door 1, but the car is located behind door 2. Now the host will open door 3 with a probability of 1, because if he can't open door 2, because he know there is a car behind it. So the probability of the probability here is 1 by 3, 1 by 3 into 1. In this case, if we stay, we'll lose, and if we switch, we'll win. If we switch from door 1 to door 2, will win. Next is the car is located behind door 3, and we are already on door 1. We have chosen door 1. So the host will open door 2 with a probability of 1. Hence the probability becomes 1 by 3, the total probability, and we'll win if we switch. If we switch from door 1 to door 3, we win. Hence, this is also a favorable case that will win when we switch. So the total probability that we will win if we switch is 1 by 3 plus 1 by 3, and which is 2 by 3. And we'll win if we stay. The probability is 1 by 3. Hence, from the theory of conditional probability, we see that we will win. The probability is higher. The probability of winning is higher if we switch.